Once again, welcome back. The great thing about doing this videos offline, I realize, is I can actually take my time and not kind of rush through some stuff. Um, this one for me might be the most important video that you'll see of this first set. Not because the rest isn't useful, vital information, but this is the subject that's least often taught, debugging. I have some logic here, and I've broken this logic in four ways, as I mentioned in the slides. So this code is available for you as it stands in the content to, let me see if I can pull that up real quick. Um, so it's called Broken Ballistic right here. And you can download this code and try and fix it yourself. You might want to stop, pause this video right now, pull up that code and see what happens. Excuse me, be able to give it a shot before you dive in too far. But I'm going to work through fixing this code now. I don't expect that you'd be able to fix this code right away, particularly if you haven't coded before. But maybe working through this example of trying to find these problems can help you develop strategies for being able to work on this better. So one thing I've noticed here, and this is something I'm not used to in working in MATLAB. If you look in my MATLAB space over in my workspace, there's a whole lot of variables left over from every single one of these examples I've been working on so far. Um, I can do it's a CLC, I think, and it clears that my command window, and then clear to clear out my workspace. Not required, but one thing to note is if I had any variables that overlapped, then when I ran this script, they might have different values than what I'd expect them to be. So that clear is kind of an important thing to make sure you have a clear environment. That's a really important thing for the debugging, because if you don't do that, maybe something's broken tonight. You turn off your machine, you come back tomorrow, you're on another machine, you turn your machine back on, you open a new MATLAB session, and then all of a sudden it works. But then a couple minutes later it doesn't work. Well, that can be due to that little extra memory MATLAB keeps around. So it's useful to remember about that. And you can even put clears into your scripts, but be careful about that. We'll talk more about that as we go. And technically, I think they don't want you to put them in for submission. So again, we'll talk more about that later. So right now, let's run this and see what happens. So as it's running, it says a ball hit at 50 meters per second at a launch angle of 22 degrees would travel 184 meters. I just realized I used 22 twice. It must be a happy number for me. And finish with a velocity of 46.1 meters per second. So in my example I worked out, I'm going to bring up this slide. That's wrong. What it's supposed to have is it's right this ball hit at 50 meters per second, 22 degrees. It should come up with 198.2 meters and finish with a velocity of 51.8 meters per second. And for some reason, my calculation is 184, so it's not going as far as I would predict, and it's not ending as fast as I was thinking. So what went wrong? Looking at the big picture, I have no idea. I mean, look at all those multiplications, divides, things to the power. That is just chaos. There's just no way I can know. So it's my job to fix it. So how can I know? Well, the first thing I can do is I can look at the variables on the side of MATLAB. And this is a huge advantage MATLAB offers, is this shows me the state of the variables at the end of everything. It doesn't show me if things are assigned more than once. So if I update the velocity multiple times, if I update the position multiple times, I wouldn't see anything but the last value, the last assignment. But fortunately, in the code we have here, everything gets assigned, I think, exactly one time. Yes, I'm pretty sure that's the case. Everything gets assigned exactly one time. So what I can do is I can parse through and work back to figure out what the answers are that are wrong. Now, to be fair, the types of questions that have been assigned to you in class so far are entirely based on your existence as an engineer and the assumption that you're good at math and you're good at manipulating formulas and that you can do physics equations or otherwise random math things pretty quickly. That's not the case in most programming. In most programming, you have to have some intuitive sense of the logic, of the rules, of the way things are supposed to work. It may be, there might not be intuitive, it might be that they're spelled out for you. But in our case with math, there's an advantage and a disadvantage. I can't necessarily look at the number and say, Well, the initial speed should have been, you know, well, okay, so initial speed y. Well, actually, let me come back to that one because that one actually is very suspicious. But the total distance underneath forward is supposed to be 202. Well, because it's 15 meters per second or meters short or something like that, it has to be the line 7 is wrong. It doesn't work like that. So really, you can either work backwards and say, okay, where did stuff break? Or you can trace it top down and say, okay, well, let's verify each line that comes along here. So I'm going to do the top down because it makes a little bit more sense to do it that way. Um, and because I don't know I haven't done the calculations by hand. If I had the calculations by hand, I could compare them, but I can do them as I go about it. Now, by the way, why am I not doing the calculations by hand here? Well, I'm handing you this code to debug, which means somebody else already put the work into it. And this is probably the first time you're reading the code. So why not do the calculations as you go along? Makes sense a little bit, right? So let's look at this first line of code. Gravity is equal to 9.0 meters. Has this launched a little bit of a tingly spider sense already? Maybe not. I've said it in a couple videos, but this could be the first video you watch. But if your physics is there, you know that um, gravity is not 9.0 meters per second. It might look fine when you look at it at a glance. This zeros and eights are both curvy numbers, but it is 9.8 meters per second. That's the first bug. It's a little bit of a gimme, but sometimes the bugs are real simple. They're just typos that come up. So if I hit the run button now, wait a minute, it's worse. It's supposed to be at 201. I put gravity at its spot. Now it's even slower. It didn't go. I mean, sorry, yeah, it's slower and didn't go as far. A tiny bit slower. It didn't go as far. So what is up with that? That is super screwy, right? Well, that means there's other bugs out there. It's not the only bug that we found. So these are constants that are inputs, speed and launch angle. Release height, you can ignore it for now, but I'm kind of like saying, okay, this is a baseball player. It's probably hitting it from about 3 feet off the ground. That's where that comes up. So then we have speed x and speed y. Now again, because everything's only printed out a single time, I can leave these semicolons on and I can look at speed, initial speed, speed x, and speed y. They're put in alphabetical order here. Or if I want to look at them as they go, I can turn off the semicolon and run it, and it'll show me the same numbers. We can see here, speed x was 18.7, and it confirms, it's good to confirm things that you think are true, that it doesn't change from the time this line of code runs, line 6 runs, to the end. So it's good to confirm that. You might be assigning it without realizing it. It might be changing without you realizing it. So it's okay to double check that. But for now, we know we can deal with the numbers that go along here. Okay, so if you go and look at these two lines of code, they look fine, right? Initial speed times the sign d, important, because we said it's degrees. Okay, so that's not a bug. We caught that, degrees up here. Sine d, as opposed to regular sine, which deals with radians. Cosine d, again, degrees, and they're based off of that launch angle, and they're both times initial speed. So this is some trigonometry, some geometry, whatever you want to refer to it as. I might double check, like, hey, maybe I have the wrong formula. So how can I double check this? Well, if I do the square root of speed x squared, let's go to the second power, plus initial speed y to the second power. Print that out right there. Let's see what happens. And the answer is 50, which is what I expect to be, right? Because these are a x and y vector portions of the vector that is the speed. So it's taking off at some angle, and this is the xy portions of that. And so that creates a right triangle. And so I just use Pythagoras right here. So I've confirmed at least that these are the right calculations. Does that assume that they're the right formula? So I'm just going to skip through a lot of this here, so this video doesn't go on too long. But sometimes you do have to check the person's code. Sometimes you have to check your own code. go back to the original formula and check if it makes sense. Sometimes intuition helps. So if I look at speed x, so this thing is taking off at a 22-degree launch angle. So is that 22 degrees more up or is it more out? If you think about a baseball being hit going a long way, it's definitely more out. So 45 degrees would be perfectly equal up and out. And so if it was 45 degrees, theoretically these two should be equal. The numbers that should be equal, the speed x and speed y. So the initial speed is 50, 35, 35. Yep, that's perfect. They should be equal at 45 degrees. So at 22 degrees, theoretically, it should be going further than higher. But when I look at this, the initial y speed is 46, the initial x speed is 18. So if I go back to the model, if I go back to not what the numbers are telling me, but what the real world, what I'm modeling in the real world, and what that's explaining, this is a problem. The problem is, and being the one who broke the code, I know it, is I mixed up sine and cosine. So maybe your trigonometric mind jumped on that. Mine doesn't. My trigonometry is very rusty. But sine is the near side, cosine is the far side to the angle. If I say it out loud, oh yeah, that makes perfect sense. It doesn't intuitively pop to me. But looking at that from the standpoint of what does this data represent? It represents how fast is it going across and how fast is it going up. 22 degrees is not a pop-up. Anything above 45 degrees risks being a pop-up. Again, I apologize for the baseball example for those of you who are not into baseball, but it works really well in this story, and hopefully most of you are familiar, if not with baseball, perhaps cricket or golf, some sport. But again, I apologize. It just works really well. All right, so when I run this, let's see, 156. It actually did it change? I don't think, it didn't change. Why didn't it change? That's kind of strange. Why didn't it change? It's because there's one more bug out there. And to be honest, right now, I forget what the bug is out there. Yes, I absolutely forget what the bug is out there, and we're kind of really into this, and I've made the point that I want to make, so I'm not going to make you sit down for a lot to walk through this, but what really should happen at this point is I should continue to walk through here. I should check the calculations. I know exactly what I did. Yeah, I remember now. So I should check the calculations, check the computations. So we talked about syntax errors. And MATLAB will show them to you right away. It won't run if the syntax errors. I'll give you little red squigglies on there. We talked about semantic errors. Well, it runs, but it gives you an error straight away. This is a logic error, a algorithm error. It's a thing that has to be debugged in the truest sense of it, because it's giving me the wrong answer. It looks like it's giving me a right answer, but it's actually a wrong answer. So the last one here, I have to work, again, line by line, work through here. So the peak time is initial speed y divided by gravity. That's actually makes perfect sense. Every second, I take off some sort of numbers of meters per second. So if I'm starting, what is it starting going up at? Initial speed by 18 meters per second. It's actually going in the air about 2 seconds overall. So in 1.9 seconds, it reaches the peak time. So that actually makes perfect sense. That one intuitively we get a feel for. The total time is the peak time times 2. So how far is it going to travel in total? This is for the x location. We need to calculate this. So it's going to go twice the peak time minus the 2 times the release height divided by gravity. So what is that all about? Well, the first thing this is all about is uncommented code, right? So I pulled somebody else's code and I look at this and I'm like, what the heck is this all about? Well, what this actually should have a comment on is this should be the twice, oops, I have like caps lock on. Here, let me put in the next line so it's easier to see. Twice the peak time, so up and back down, plus the extra release height. So if you're standing on a tower and you throw a ball, it's going to go a lot further out than if you're standing on the ground and throw a ball. So if I hit a ball a meter up, it's going to be way different than if I hit a meter up, if 100 meters up. So one way to test this is if I move my release height from 1 to 10, all of a sudden it traveled less far. That makes 0 sense, right? So if I throw a ball from the top of a wall it should travel farther, not shorter, right? If I throw it, if I'm standing in the back of the bleachers and I throw a ball, it's going to travel much farther than if than if I'm standing on the ground. So let's go back to one release height. So maybe if I look back at the formula, what I would find is this should be, oops, yeah, plus the release height, not the minus release height. So that should be bug number 4. And I remembered how I broke the code. And I didn't want to get further into the nastiness here. But now you can see traveling 198 meters and a velocity of 51.8 meters per second. That actually aligns very well with, perfectly to be frank, with what I expected it to be. So 198 meters, 51 per second. Um, Last tiny little nugget I wanted to throw out here before I leave is this problem also shows how my model is really, really poor for describing what I really want it to do. Because, think about that. This hits the ground faster because of that extra 1 meter of falling than it left the bat. If it did that, how dangerous would it be to fans in the stand? If the ball, you know, well, it probably wouldn't be faster, but it would be almost as fast as what it left the bat. And the bats, you can leave the bat at 100 and some miles an hour. So I wanted to show you a quick check on this. This is from MLB StatCast. This shows the launch angle and velocity of balls. So uh, the 100-mile-an-hour pitch, I think, was about what I was talking about, at the 50 meters per second right there. And so if I have a 100-mile-an-hour pitch that I hit at a 22 degree or 16, well, here, 100, yeah, there you go, 104 at 20. Almost all those balls are home runs. But if you look at these home runs, the long distance is 410 feet. 200 meters is 600 feet. So if you're hitting baseballs in the moon, they might travel 600 feet. But with air resistance, they're not going to get anywhere near that. So it's going to take a third of the distance off of what we're seeing in our model. And so our model, even though it's working perfectly correct and the math is perfect and everything's working just as another website I looked at gave me answers for, because I want to double check my answers, and it was a calculator website. It wasn't a cheat for this problem. It had a calculator for ballistic trajectories. This model doesn't work real well. I wouldn't use this model to, you know, do a simulator for a baseball game, because I would have to include wind resistance, air resistance in some form for this. So the main point of this is debugging, working through debugging, how we use the environment to look at the variables, look at values, compare it to the values step by step, what I expect it to be and what's actually happening. But what I expect it to be is formed based off of a model, both on what I'm trying to represent in equations and also what's going on in my head. So hopefully this is a valuable idea of how to not only fix your code, but make sure your code is meaningful as you work forward on the projects to come later in class.